As I told you, we will give you a basic introduction to your IoT ecosystem. What are the different components inside it, and basically focus mostly on the architecture side. First, I will try to focus your attention in the among the huge number of startups that are in this space now, right? If you see, this is an analysis of approximately, it's written about 2K, right? 2,000 IoT startups, and they have nicely categorized them into different kinds of companies, starting from hardware platforms to software platforms. People who are working on the drone space, drones and robotics, fitness, right? Fitness is something that is pretty much in, and apart from that, you also have this in this smart homes, right? You have this Google Nest and so on. So different kinds of applications. I would request you to spend some time by looking into these different verticals where IoT comes into play, and try to look at what these companies are like doing, right? That will give you a lot of idea about this space, right? Because some of these uh, problems are really, they have kind of understood like what space of problems can be solved using IoT systems. So the kind of things they do, that gives you a very good idea about what are the pressing problems in terms of, in both from the interest of industry as well as as well as an academic interest, because some of them are really good startups and they do a lot of uh, write a lot of research papers and so on, right? So sometimes those kind of things will help you to gauge the market, as I would say. So this is a formal definition of IoT, right? There are lots of definitions out there in the internet, but this I specifically picked up because it covers a lot of grounds, right? If you look at this carefully, what they are saying is this is being defined as a global infrastructure. So one of the visions of IoT based system is that there is a global interconnection in between these embedded computers, right? Which is needed for the information society, and they are enabling advanced services, right? It's not just the typical services we used to have in regular computer based networks, like booking an air ticket or booking a movie show and so on. That this is much beyond that, right? And how is it enabling those advanced services? They are trying to do it by interconnecting physical and virtual things. So this is important. So they are trying to connect both physical and virtual things, uh, and based on existing, right? So and evolving interoperable information and communication technologies. So we have to understand the space that it covers, right? So first thing that is interesting is it is trying to create advanced services by interconnecting physical and virtual things. So this is important. So earlier, what we had to have in a computer-based network was basically everything was in the cyberspace, everything was virtual. Whatever you had, like whatever you interact with the computer, be it booking a movie ticket or booking a railway ticket, everything happens in the remote database, right? So there was no physical device or an object, right, that was directly interacting with the cyber world, with the cyberspace, right? All you had was this keyboard and mouse, right? And that is everything. So now what we are talking about is advanced services. I'm going to give you an example, right? I have a small demo that will help you to understand that better. And another thing which is important is evolving. So sometimes what happens is, based on the interaction, there are new virtual objects that are created. If you are playing, let's say, a game, you are making, let's say, hand gestures and trying to control something in the computer, in the game, right? So the situation evolves, right? You create something, you destroy something. So the virtual space is also evolving, right? So existing and evolving, and they are interoperating among each other. So you can pass an instruction from the physical space that actually manipulates things in the virtual space. So this is something that is also very important. And if you think more about it, you'll see there is a lot of research that goes on in this field called HCI, or human computer interfaces, which makes use of this very fact, right? What are the new modalities by which human beings using physical objects can interact with entities in the virtual space? Okay. And then there are respective information and communication technologies. Of course, communication technologies are important here because uh, all these things like the data rate, right? How much of information is being passed from these physical objects or the devices that they are performing the sensing operation. What is the bandwidth that is required? How much of latency is tolerable? Or what is the distance that you can actually support in between your IoT device and the gateway device, let's say, or the physical object that you are interacting with, right? So the communication technology play a very important role, and maybe you have heard of systems like LoRa and Sigfox, or even BLE, Bluetooth Low Energy, and Wi-Fi that are pretty much used in the IoT space. Okay. So what do we mean by a global infrastructure? It's the same example that I sort of showed you last time is the temperature sensor. And once the temperature sensor has this GPS coordinates available, one of the philosophies in the IoT space is to realize a global infrastructure of the sensors, right? So you can make any query about a particular location, what is the temperature around that space, or in fact you can do any prediction, right? For example, you are getting the temperature data from n number of locations, and using that data, can we do some kind of a prediction, right? So those sort of also comes under the fold of this IoT infrastructure, right? So as I told you last class, we'll mostly concentrate on the sensing computing part, maybe to some extent into the networking interface also. But again, if you try to define the IoT ecosystem as a whole, these are the things that you should also keep in mind, right? What are the different components that go there? So if you look at the network interface of this IoT device, there are things called messaging, right? So there are messaging infrastructure. Right. So you need to pass control commands to the cloud, as well as you will receive control commands from the cloud. And there are a whole bunch of ways to do it, right? There are different uh, components to it, right? One of the example is, if you have not heard, there's something called MQTT, right? This is a publish subscribe mechanism by which you can exchange data. IoT devices can exchange data with the cloud database. You can write data, and there could be control instructions coming from the cloud end, so that it asks you to do some operation. Okay. So this is one example, and in the class or as a part of the project, we will explore more about it if you want to integrate your IoT system to the cloud, right? Okay. So this is one kind of the vision, right? If you look at the definition, so we spoke about the global infrastructure. The other part, which is important in our aspect, right, if in the with respect to this class, is interconnecting physical and virtual objects, right? That is something we will deal with every day, right? Yesterday, for example, I showed you this video of me jogging or walking in front of the sensor. So basically, whatever I am doing, right, all these physical activities of the environment or the subject, in this example me, are being picked up, right? So that is some kind of an interaction between the physical and the virtual object, like worlds, right? So this is another example where I have created this keyboard kind of thing, right? This is complete, there is no electronics actually in this keyboard. All of this is a cardboard, and on top of that I put some aluminum foils and just attached a bunch of wires to them, right? There is no switch, or there is nothing else. This is a purely physical object, right? And I'm trying to show that what I mean by interaction in between physical and virtual objects. So let's see here. This is, I'll show you the connection. This is connected to some kind of a sensing device. We'll learn about this more later. This is connected to an Arduino, and see here. Yeah, so I could actually touch, right? So I'll stop the video for the time being here, right? So if you see on the top, you can see a computer screen. I have cropped it, but there is some application that I have written which somehow translates your touch from the physical device, in this case this is as simple as a cardboard, to some kind of a translates this into the digital domain. right? So they can understand if I touch this third aluminum foil, this translates to the block number 3 in the virtual world or in your computer world, right, in the digital world. So this is the kind of interaction that we are talking about, and this kind of interactions actually helps you to develop evolving interfaces, right? You can do something extremely smart, right? So if you want to do pass on very complicated commands without writing lots and lots of code, or enable some kind of automation, this is the way to go, right? So you note that we are not using any explicit like switches or things like that to enable this operation, right? So in theory, instead of these aluminum foils, it could be really anything, like any object that I will teach you in details when we talk about capacitive sensing and so on, right? So as you are seeing in this example, when I touch 4, it goes to 4, and I touch 5, and so on, right? So this kind of a clear interaction in between this, and then based on this simple logic, I created a reaction kind of a game. So whenever the 7 is marked, you have to basically touch that switch, right, or touch that aluminum foil, so there is a hit, otherwise there is a miss, right? So it's a very simple thing, not that useful though, but just to demonstrate what it means by interconnecting physical and virtual objects. Okay, so yeah. Uh, so note that as I'm focusing more and more on the sensing part, here the physical object does not have any electronics. All the sensing is being done by the chip that I showed you, as well as the processing is done in the Arduino board. Okay, so don't go into the details of how this works. We will actually cover this in later part of the semester, right? And we'll have much more. This is just a preliminary thing.
Sir, so you said there's no electronics involved, but you said there's a sensor near the Arduino. So the concept is, if there's a big wire and the sensor is somewhere else, or is it under the metal piece?
No. I'm trying to say here, yeah, you are right. What we are trying to do is we are trying to give this intelligence in the physical object, right? So not only I am trying to detect whether it was a binary touch, right? Whether you are touching or not touching. We can do much more with it. How hard you are touching, or whether you are swiping your finger on top of the aluminum foil. Even those kind of things are possible without having any extra sensor, right? So there is nothing else here, right? So I'm trying to say that this is a physical object, right? And then there is a sensor which is acting as a gateway in between the digital world and your physical world, right? You have to connect them some way.
Yes, sir.
Okay, so that's what I meant to say, right? Even if it is a chair or a table, you can do the same thing, right? If you are connecting something to the chair and somebody sits on a chair, right? You can have the same thing without having any electrical connection between the person and the chair.
Sir,
Okay,
so if those aluminum foils themselves are like some force sensitive resistors or something, would it not be called IoT there?
if the aluminum foil,
Like instead of like under the aluminum foil, I have now stuck up a force sensitive resistor directly under it.
yeah, of course. Yeah,
So
you have to have 8 force sensitive resistors, and you can do all those things. Yeah.
yeah, so will that be the same as this one? Can I call both of them IoT?
Oh, of course, yes. I mean, both of them are sensing systems, right? And now, if you are connecting them somehow, right, it still becomes IoT. It's just the modality is different, right? Whether you are using a force sensor or whether you are using a capacitive sensing. So these are different modalities to do the same thing. What matters is what is your cost budget, what is the accuracy that you require. This kind of things start playing a role, or how much it is scalable. If you have 100 switches, can you do that? Right, whereas if we have 100 switches, we can do something intelligent here, right, without having 100 sensors. So next is I'm trying to give you a basic introduction to the IoT system architecture. So what are the different components that are involved when we talk about IoT based systems? So first we start with IoT devices. So these are the devices with the least amount of resources, right? Least resources. Okay, so these are basically the embedded systems that we are talking about, and these are the devices which are actually sensing or doing some monitoring task or surveillance task and so on, right? So these are the devices that we really care about, right? These are the devices in your actual field. Okay, now we have this series of devices that are deployed before the data actually goes to the cloud, right? There is a storage in the cloud, and all these analytics and visualization are still okay. And anybody wants to give a try about why do you need this series of devices? Why don't you directly connect these IoT devices to the cloud, right? Is there any rationale behind it? Why does your computer network doesn't look like this, right? You can directly connect your computer or your smartphone to the internet and start sending data, right? But for IoT devices, we normally propose this kind of an architecture. Anybody wants to give a try? What is special about these devices?
Because they can decide which data to send to the cloud, or which data to process there only.
No, I didn't understand.
Sir, I'm saying this device can decide that whether the data collected from the IoT devices should be sent to the cloud, cloud storage or not. Do some filtering we can.
Yeah, sir.
No, no, no.
Since you mentioned that IoT devices are having the least amount of resources, sir, the gateway devices might be used for interfacing and maybe encapsulating data in certain format and transacting with the
Right.
It's a number of devices would be high, sir. The IoT devices, sir. So
Right, right.
So that is the reason we make it serial.
Yeah, it's not just not only the number of devices, the number of smartphones is also high, the number of computers is also high. That's not the reason. The correct answer is somebody gave out is about the resources, right? These devices are very specialized devices, right? We are not running a Linux stack on top of this, right? We are not having, even we might not even have things like Wi-Fi and so on in these networks, right? And they might not even have anything like IP-based addressing, right? The packets they are creating might not be even IP packets, right? So if we want to really run a network stack, right, what we need is a complete TCP IP stack, right, in order to communicate these IoT devices to the remote cloud, right, which is sometimes extremely expensive in terms of hardware support as well as the amount of energy they will spend and so on. So, and also the other thing somebody mentioned about this encapsulation. So often we need to encrypt the data. It could be medical data. So often we need to run some expensive security kind of algorithms, right, in order to make the data secure. And then once these things are done, then only we want to transport this data to the public internet. So that's why we have this series of devices. First of all, there is a gateway device. Often the gateway device will reside in your home if it is a home-based system of IoT devices. Suppose you have a smart TV, often like Samsung smart TV, often had this historically. They sometimes had this gateway device, right? So any IoT system that Samsung sells is going to connect to that gateway device, and your television is fairly has much more resources compared to your smartwatch and so on, right? So they will try to do the computation there, right? And whatever encapsulation or any other security algorithms that they need to run, that can be run in the gateway device, and which will be exported outside your premises, right? It could be outside your factory or outside your warehouse or your home. So that could be the edge device. That's typically known as the edge device, which often belongs to the ISP, right? They will the internet service provider, they might even have this edge device which takes the aggregated traffic from all these gateway devices. There could be other gateway devices belonging to other entities, and they basically get this aggregation of this traffic. And all this traffic might have different priority levels. Some of them could be latency sensitive, some of them could be more dependent on bandwidth, and like the different things like this, right? So different priorities for different traffic flows. And then finally you have the storage where all this data is finally written, and you might have analytics and visualization and so on. And you could have these end users who can also directly pass on commands, right? It's the same way. So this is, if it is a secure interface, not everybody can pass on commands and then directly manipulate the IoT device. So all the security mechanism are somehow built in this pipeline. So IoT security is also another great field where people try to look at how can you make this very resource limited devices more secure, right? We cannot afford to compute a lot of memory or computational jobs on these devices, but can we do something else to secure this entire ecosystem? Okay. So given this, we'll start with the basic functionalities that IoT device wants to achieve. The first one is sense. Of course, it has a bunch of sensors, and one of the primary functionalities of an IoT device is to perform sensing tasks. And based on the sensing data, what we try to do is we try to do computation, right? It might need to process the data and send some of the data out, or maybe all the data out, depends on the application. And then as I said about sending the data out, this is about the comms, the communication interface, right? It can either send it out or it can do some actuation, right? It can drive a motor, or it can drive some LEDs, or it can drive a display, and so on, right? So these are the three things that are primarily done in a IoT based device. Okay. And this is a general architecture, right? If you have a thing, right? So that's why I have written. So this board is nothing but some device that you want to, something that you want to connect to the internet rather, right? So that it becomes a part of this IoT ecosystem. So these are the several things that you actually require. You require a bunch of sensors, or like a dedicated set of sensors that is useful for this particular application in mind. You have this microcontroller that we'll talk about today. Then you have this bunch of things for communication, a radio, an actuation device, right? If it is you are trying to, it is a robot and you want to control the servo motor and the stepper motors, and you might have display optionally. And one of the important things is also you need to provide power to this device, which is on its own right is a very important research topic, right? So the how to power an, okay. So one of the example that I've shown on the right hand side is of a drone, and as you see, there are these different components that we actually associate with this drone, right? We have this radio, we have the bunch of sensors. It could be for example, an obstacle detector, an ultrasound sensor, and so on. There's an inertial sensor also in the drone. You have these actuators, which are nothing but the propellers, which are controlled so that the drone maintains a stable flight. You have the radio, which is used to pass control signals from the ground, or even send any control information feedback from the drone. And then there is a central brain for the flight controller, which is basically the microcontroller, which is controlling every aspect of the drone's movement, right? All the computation is being done there. So in this course, we'll primarily focus on the microcontroller and the sensing aspect, as I told you, and not much on the powering and the communication systems per se, right? So powering itself, there is a lot of things. How do you run these devices on like zero battery, right? Completely based on harvested power. So those are like very, very interesting things to do. And some of you, if you are interested in pursuing things like powering something completely based on harvested power from ambient energy, ambient wireless signals, right? You can explore them as a part of your project, right? So there are microcontrollers like if you have heard of MSP 430, this kind of microcontrollers, right? They're very, very low power microcontrollers, right? So they can be actually run by harvesting ambient energy. Just from thin air, you can charge a capacitor and then use that charge to run this microcontroller, right? So we are not going to cover those in the class, but yeah, of course, if you are interested in this domain, you can explore that as a part of your project. Okay, so why bother about these things? All of these devices have one thing in common. They have different categories of microcontrollers, right? Some could be very not that resource poor, and some of them could be a very expensive on the higher end microcontrollers, right? With like huge amount of memory and so on. So there is an entire spectrum of microcontrollers that works in this kind of devices, right? And my task in this course is to give you an introduction to what is the common in among all these microcontrollers, or what is the rationale of their functionality, and to give you an introduction to embedded system programming, right? So that you can actually write your own code and test some functionalities out, right? So a very simple introduction I'll give you about microcontrollers. Let us be interactive. So if I ask you something, if you happen to know the answer, we can interact, right? So this is again a replacement for a computer organization and architecture class, right? So if you want to go into really details about these things, you have to take a course on computer architecture, right? So this is a bare bones that I'm trying to cover so that you have a meaningful introduction for the rest of the codes and the sensing when you try to implement, right? So that you understand what basically is being done, right? But if you have interest, you can look up more in an architecture kind of a course. So we'll start with the basic building blocks inside a microcontroller, and we'll start with this arithmetical or logical unit, or there is a processing unit, right, which has all these different functionalities, right? Circuit 1 serves one function, circuit 2 serves another function, circuit 3 serves another function, and so on, right? You can have this processing unit which has this n different functionalities, and if we give an input to one of these circuits, it is going to evaluate, right? It is going to run the operation that the circuit is intended to do, and then give out an output. Okay, and how can we control? Basically, we need to control this sequence of circuits. We need to tell that whether to turn on a certain functionality or not. So you can do that using passing separate instructions, right? Suppose I want to have operation 1 activated, so I can just say that turn on operation 1, and the circuit 1 would be on, and based on the input, your output would be the output of circuit 1, right? Rest of them are sort of switched off, right? So as to say, so if you encode this information, I'm basically saying turn on operation 1 and turn off all the other operations. So 1 0 0 0 0 up to n is going to switch on the functionality 1. So whatever is the input is going to go to circuit 1, and you will get the desired output. Same for if you are trying to use operation 2, you are going to do something like 0 1 and rest of them are zeros. This is just a encoded way of representation to the computer, right? So suppose you have a bunch of switches, you have n switches, you turn n minus 1 of them off and turn on one of them, so that the computer knows what is the desired operation the person needs to do. And so for all n, right, you can have these things. So in a nutshell, what this basically comprises of is called the instruction set, right? It is much more, so this is the naivest way of introducing you to the instruction set. So the set of instructions that the computer understands. So you have a processing unit which has these different functionalities, starting from the circuit 1 achieving the task of function 1 and circuit n achieving the task of function n. So function n could be addition, function it could be multiplication, it could be a logical operation. For example, you can try to do a logical AND or logical OR of two input data, right? So each one of them has a segregated functionality, and all your instruction set does is, or each individual instruction does is try to dictate to the computer what functionality to do at this current point of time, right? So you cannot have all of them at one point of time. Given the input and you tell the computer what to do, it will do that. Okay, and the collection of all these instructions is known as the instruction set. Okay, clear. And you won't be using all the instructions in a program, right? So there could be, in this case, if we try to see if it is you are turning one of them at a time, you might have just n instructions in the instruction set, right? We are not using any combination of them, let's say, right, hypothetically. So a program that you are going to write will have a combination of this n instructions that you can pass on to this computer, which is known as the machine code. That if you pass on this machine code to a computer, it is just going to execute this instruction one by one and give you a desired output, right? For every instruction in this example, we are expecting an input. the input could be null, right? There could be no input, or you can optionally give an input, right? I'm just talking about the example that we are discussing here, right? The general thing is much more complicated. Okay, so this is basically what comprises of the machine code. And what we do is write a high level program. It could be C, it could be C++, where we have this list of functions, right? We want to execute function 1, so function 1 is executed, right? We give the input, the compiler compiles all these things and creates these instruction sets, right? This comprises of this machine code, which directly the computer is able to execute. We are going to see how. Okay. So next is, I would say, as you have already figured out, right? So the functionality of this kind of a system is too limited, right? Okay, somebody want to give a try? What exactly we are missing? What are the most important things we are missing here? Or it's not optimized?
Logical unit, sir.
No, let's say logical unit we have. Let's say circuit 3 is a logical unit, right? These are all combinational circuits, right? So it can do an addition, it can do a subtraction, it can do multiplication, it can do some logical operation, not a problem, right? But I'm asking about the general way I am presenting these things, right? What is something that we are missing out? Just the instruction set is fine.
A clock.
What? Sorry?
A clock.
A clock. Okay. So, but let's say we are trying to execute one instruction.
So there is no parallelism right now.
No, we don't need parallelism. It's a simple thing.
Storage.
Yeah. So yeah, some of you, I'm not able to see who is responding, so you can tell your name even while you respond.
Shamjit.
Okay. So yeah, there are primarily two things that we are missing. So let me put this out. So there will be like too many functions and circuits, right? And you are basically trying to assign 1 bit for each of the functionalities. So one problem is that the size of your instruction keeps on increasing, right? You need to encode it in some other special or clever way, right? And the other problem is that you might have some operations which actually could entail a combination of the circuits, right? So suppose you want to do addition or let's say a multiplication, which could be executed as like a repeated addition, right? In your CPU, you might not have hardware for doing multiplication, right? Or let's say a floating point multiplication, for example, right? You might not have hardware support. So in that case, what you need to do is you need to somehow take the help of other circuits and build the instruction in that way. Okay. So sometimes they are not independent of each other. Sometimes some of the circuits have to work in unison in order to achieve a certain high level function. That is number one. So you might have many instructions which which we basically use to create the optimal combination, right, for a certain functionality. The second thing is that there is no way to manipulate inputs and outputs, right, over a series of operations. So somebody has mentioned storage. So one of the fundamental things that you require in a computer is to do successive operations, right? You want to pass an input, get the output, and that output has to be passed on to another input, right? When you write a program, you are using variables all the time, right? So the fundamental concept of these variables in a program is there should be a way to store them, and access to them has to be guaranteed during computation. You add two numbers, you have to keep the result somewhere, right? And not only when you try to add two numbers, you need to read the input from somewhere. So this is a very integral component of your the way you are designing your instruction set. If you say add, right, the computer doesn't know what exactly to add, right, whom to add. There are so many numbers out there in your registers and in your memory. Okay, so the instruction should also have the ability to manipulate inputs and outputs over a series of operations. So again, we start from the same point, right? We have this input, we have this series of circuits and output. Now, instead of enabling an individual circuit one at a time, what we have is we have a series of instructions, right? This instruction could be actually activating 2 or 3 circuits. We don't know, right? it can try to do something with the inputs, or it wants to write in a particular output. So those things are taken care by something known as the instruction decoder. Okay, so all the instructions that we gave earlier, like that 100, let's say now we can have a combination, right? So this goes to the instruction decoder, and the instruction decoder decodes this 100101 into what it needs to do, what circuits it need to activate, and so on, right? So does this need to read an input? Does this need to read an output? Where exactly the output has to be written? Where exactly the input has to be read? Right? So that information has to be encapsulated in the instruction, and the instruction decoder's job is to decode that information. So let the hardware of the processing unit know, right? That is what the program is demanding. So you can have all these m instructions that is possible in a given computer, and now this becomes your instruction set. Right? This is instruction number 1, instruction number 2. These are the m different instructions that you can instruct the hardware to do, and the instruction decoder with this piece of hardware that is going to take this instruction and signal the appropriate parts of the processing unit to do the processing execution, right? And your program, your machine code is going to have a combination of one of these m instructions. So you'll have, for a given program, you will have, say, instruction number 3, then instruction number 7, and so on, right? This comprises of your machine code, right? We will see how this machine code is executed within a short time. Okay, so any questions still here? Any problems to understand what kind of instruction we had earlier and why we needed this instruction decoder?
Hello.
Hello.
Hello?
Yeah.
Sir, at your time, so many instruction will come at your time, no? So data will miss, no?
Yes. So we'll see how to do. Basically, the next part is how to deal with that, right? So many instructions are there. So what should we do? We should do them one by one, no? So how to do that is I'm going to discuss, right?
Okay,
So
okay.
Currently what I have done, let's say there is only one instruction in your computer, like in your program, right? Let's say add A and B. That's all.
Okay.
Okay. So I'm talking about the instruction decoder, which is taking into this input and signaling the appropriate parts of your processing unit to do that. And next comes the temporary storage, or the storage of your the CPU needs something to write this data to, right? It can read from there, or it can write to it. So this is a CPU specific storage. Within the processing unit, you have this set of memory locations. These are called registers. This could be 1 byte or 2 byte, depending on the type of microcontroller we are talking about. It could be a 16-bit register, it could be a 8-bit register, it could be a 32-bit register, right? So this is a location where we can temporarily write data, and your this hardware that we are talking about, the CPU, is continuously going to probe that, right? Once it wants to read something, it is go to register number 4 and read out this data, go to register number 7 and read out this data, add them and put the result in register number 11. So that's what they will do, right? That's what that the instruction sets is going to tell them. Okay, so somehow, as you are seeing now, we also have to encode which register the data is going to as a part of this instruction. We'll come to that later. And again is the memory part, right? So sometimes the amount of registers that you have in a CPU is very limited. You might have 32 registers, or you might have 62 registers, 64 registers, and so on. But this might not be enough, right? You actually have to add a lot of numbers, or maybe you have a censored data which is being written to the memory, and you need to read them out one by one. Or suppose you want to write back the data into the memory for permanent storage and so on. So you can even do that, right? So somehow we also have to have access from the memory location. Okay, so register is one kind of storage, and this MCU storage is the microcontroller storage, right? So we are going to discuss elaborately about memory, what kind of memory is there, what is SRAM, what is the EEPROM, and so on. But you can just for now think that there is a memory which is outside the CPU, and there is a memory which is consisting of registers inside the CPU. Okay, so this is a CPU storage where you can read and write and so on. And now it becomes clear that we have to have this instruction that comprises of these three things. The instruction has to have a purpose. What it is doing, is it trying to do an addition, it is trying to do an AND, it is trying to do a subtraction. It has to have some kind of basic purpose, right? In terms of functionality, right? You can say in your program you write f, right, a function, right? You want to define a function and you pass on arguments. So similarly, as a part of your machine code, we also try to have this operation, which is the purpose, and where exactly is going to operate this instruction on, where is the data coming from. So the data can be read from a register. So RS is the source register. It could be anything that would be encoded in your instruction. It could be R3, R4, or depending on the number of registers that you have in that particular microcontroller. Or you can also read from memory. So there are ways to directly access the memory, and it varies. The functionality varies from vendor to a vendor, but most of the microcontrollers help you to give you an option to directly load a memory location into your register. So it's, you can read a memory location to your register, then do an add operation, or even directly fetch from memory and do the add operation. As well as same thing holds for writing back, right? Once you are done, you want to write that information out either to a register or a memory. So this is basically the skeleton, okay, of an instruction. So yeah,
Sir, one small doubt, sir, in the last.
Yeah, go on one by one.
Yeah, shall I go ahead, sir? Simply.
Yeah. I'm not able to see anybody. So
sorry, sir. In the last slide, sir. So the instruction decoder is directly connected to the circuit. Would it be like the instruction decoder decodes the instruction and put it in the register? From there, it has been read by circuit, or it goes to the circuit and then goes to the register, sir?
Yeah, there are certain steps in between. I drew this picture for you to understand without introducing a lot of complexities. Okay, so instruction decoder's only job is to understand what to do, right? Okay. And then there are other things that comes into the play. So I'll try to explain how a program is executed, like after one or two slides.
Okay, sir.
So hold on to this thought, right? So yes, you know that there is a certain hardware which can recognize, right? This is like a gatekeeper. It recognizes a valid instruction and invalid instruction.
Yes, sir. Yes. Okay.
Sir, I have one doubt in this slide. This is Shubham Samant. Mm-hmm. Sir, does the instruction set architecture have an impact on how this process happens? For example, if there is a x86 architecture.
Yeah, I have not introduced the architecture set, but yeah, you can still go on.
Okay, sir, just have two questions. In case today we hear things like system on a chip, or one step ahead, things like system in package. Something like an Apple Watch. So is this still template remains the same for across the devices, or this fundamental template itself changes as and when we shrink the technology down?
No, yeah. So this is something which is very fundamental to something called a microprocessor, right? So microcontroller is at least one step ahead, right? So it's packaging the entire computer on a single chip, right? And once you talk about SoCs and so on, you actually keep on adding functionalities in that chip, right? For example, Snapdragon, Qualcomm is creating all these SoCs, right? So they have even radios and other functionalities packed on to that particular silicon. Okay, so the instruction is something which is extremely fundamental to the microprocessor.
Okay, sir.
Okay, so it could be a Qualcomm microprocessor, it could be a Intel, or it could be Atmel or Texas Instruments and so on. But this is a philosophy, right? How instruction sets are executed and decoded and so on. So these things doesn't change.
Okay, sir.
Okay. So there are fancy names to it, as I was talking about this read from and write to. So opcode is the purpose, right? This is your add or sub or multiply or right or and lots of things, right? There is something called XCH, right, in Avr architecture. So you can exchange, you can swap two memory locations, right? And this is something where the data, what is the data that is going to operate on, right? These are the operands, right? किसके ऊपर काम करेगा? It's like the data. So these are the operands, and it could be one operand, it could be two operands, and so on. Okay, and there could be like something like no operands at all, right? Suppose you want to say sleep, right? So the computer sleeps, no operands are required. Okay, so your instruction decoder understands all those things, what to expect and what not to expect, right? And if something that is illegal, right, you have sent an instruction in the machine code that doesn't mean anything. Okay, so this is exactly the same thing that I told you right now. So now this is your instruction set. Some of the instructions require operands. For example, if you want to say add and just give one operand, it's not going to, it's kind of an illegal instruction, right? So your instruction decoder won't be understanding anything. So it's basically going to take the next byte and add them. Okay, so there is not much intelligence here. Right, so some of them, as I told you, can have 3 or 2 and so on. So as I said, instructions are normally 16-bit long word. So it could be, in case of AVR, if you see, there are like 16 bits long, and except for those, that is including an address. So if you want to add 2 memory locations, so you have to give the address of that from the flash memory or from your SRAM, right? So if you are using an address, of course, the size of your instruction becomes bigger, right? In that case, you might have 32-bit instructions. Okay, so ideally it is encoded within 16-bit. And if you look at the manual, I'm going to show you some examples from the manual where most of it is like we can satisfy package the purpose or the opcode as well as the operands, as long as it is limited to registers, right? We can mention which registers to read from. There are about 31 registers here, so 5 bits is enough to identify one register. Okay, so here I have given the same example. So sleep does not have any operand. Decrement RD. So whatever data is written in RD register, it will be decremented by 1, right? Similarly, you can have XCH is basically going to exchange the data in between register number D or the destination register, and ADDR is some address location, right? So whatever was the data that is written in that particular address is going to come to RD, and whatever was there in RD is going to go back to that particular address. So this is something that I don't want to talk about in details, but we are going to mostly deal with RISC class of processors. So this is called reduced instruction set computer, where the number of instructions are, or the type of instructions are very simple. As I told you, the example of floating point multiplication, that could be a very complex instruction, and it could actually entail a lot of sub instructions, so as to say, right? In a simple computer, you just do an add, right? That's all, right? And most of the instructions are that simple in nature. Okay, these are highly optimized, and the code that you have to write is long, right? Because most of the instructions can do very simple jobs. So your program length will be very long, because the hardware does not handle any complication. It's not going to do a floating point multiplication. You have to implement that in software, and then in your assembly code or in your machine code, and then for example, the repeated addition, right? You have to write a while loop and keep on adding those numbers. So add is the hardware functionality that it gives. Whereas in a complex instruction set computer, individual hardware instructions could do much more complex jobs. For example, floating point multiplication, right? I would ask you to look at it in more details, particularly if you have a background on organization and architecture. Otherwise, you might just take a glance even at the Wikipedia page. That will give you some details about the differences in between RISC and CISC architecture. In all the low-cost embedded systems that we are talking about, starting from Arduino kind of processors, right? The Atmega 328, the Atmel, these all use RISC instruction set. Okay, the reduced instruction set computer. These are examples of RISC processors. Okay, so if you want to know more about it, you can ask me if you have a confusion, but I'm not going to go more into this because of the flavor of the class. So just to get familiar, right, I would ask you to go through the instruction set of Avr microcontrollers. So this is something that is used in Arduino, and it's a very common microcontroller that is used in many embedded systems, right? 8-bit Avr microcontrollers. And for example, you can just look it up. Just type in Google Avr instruction set manual. It will give you this, and you can skim through them, right? How the instructions look like. And looking at the manual will give you a very authentic way to understand what happens. What are the registers that are affected, right? What exactly is the size of the instruction? What is the opcode? What are the operands, and so on. So here I have given you an example of AND operation. So this is a logical AND operation. The operation looks like this, right? AND RD and RR. So there are these two registers. RR is one register and RD is another register. What it does is it does an AND operation and writes the result back to RD, destination register. So in your machine code, the 16-bit thing that you have to write is somewhat like a combination of all of them, right? It captures both what you have to do, the AND operation, as well as the registers, right? It has to know what two registers has to AND. So some of this, the way they encode this information in the instruction is very complicated. See, if you there are 31 registers, so the register address can be expressed as a 5-bit number, right? This is also our 5-bit number. So 5 plus 5, 10. And out of this remaining 6, they are somehow distributing these numbers like this. So some of the numbers are lying here, right? And then another part of the R is lying here. So here you have 4 numbers, 4 bits, and here you have 1. So in this way you get 5. And for D, you are again having 5, 1 here and 4 here. Right? For some strange reason, for some optimization they want to do across the entire hardware, they will design the instruction set like this. Okay, and if you see the first part, this basically tells the instruction set decoder that it is an AND operation. Okay, it's an AND operation, and when they will decode it and try to know that, oh, this is an AND operation in between RD and RR. And after that, even write the result back to RD. Everything they will know. This is defined in hardware. Okay. Similarly, this is instruction. These are an instruction where both of this memory as well as registers, both of them come to play, right? So LDS is called load direct from data space. So data space is your memory, the SRAM, where you have to give an address, right? So K is the address and D is your register location. So RD, you will again require 5 bits. So you'll see 1 bit is here and rest of the 4 bits are here, right? And this tells the computer that this is a load data operation. Register is this, and when you read the next 16-bit, it is going to give you the 16-bit address. So this K. So basically, it could be, let's say, 26FE, right? This is an address in hexadecimal format. So 26FE is a memory location. So it will tell you to load the data, whatever is written in 26FE, to the register R7. Okay. So it will be like LDS. If it is a register 7 R7 0x26FE. Right now you have to encode this, what it is exactly going to look like in your machine code. Right. That is what the compiler will do. It's converting to assembly language, and that assembly language code will be written as a machine language, right? The ultimate thing that is the hardware is going to understand looks like this. Okay. So there are more things like program counter, PC, and so on. I'm coming to that. So now you give an example, right? So you know how the content in your memory is actually, it has an address space. So all the memory locations are having some kind of an offset. It starts from 0000. In this case, this is a hypothetical example, and all of this thing, right? Let's say I can store 1 byte in this content space. So all of them has an address. If I say 0001, it's going to point here. If I say 2E97, it's going to point here, right? So let's say you have this program that you want to execute. Okay, so this program has to run in your the computer that we are talking about, and it has to give you out some results. Okay, and the program starts from memory location 2E0 to E97, and it continues to 0 to E9B. Okay. So by the way, what is the size of this memory? Anybody? I have like FF. There are 5 Fs.
So is it 8?
What do you mean by 8?
8. No, it's not 8-bit.
Yeah, I'm not going to give out the answer anyway, but yeah, there are like 60 plus students in the class. Anybody can answer. So this is something extremely fundamental you need to know.
20 bits.
How many bits are there? 20
20.
bits are there. Okay. So what is the size of the memory?
1 megabyte.
Exactly. Yeah. Thank you. So you have like 10 bits, right? That is a 1 kilobyte. You have 12 bits, right? So 12 bits is 2 to the power 2. So 4, and then 1 kilobyte. So 4 kilobyte in that way. So just by looking at the address, you should ideally know how much of the memory address you can actually refer to. What is the size of your address, right? So this is very crucial. When you talk about these sensing devices, they are sending this data. You are trying to store those in your memory, right? You really need to understand where you are trying to store this data, right? You have to have a good idea. Okay. So now what I did not mention was, like we were talking about that one instruction is just being executed, but in a real program you need to execute tens of instructions, hundreds of instructions, right? Or sometimes millions of instructions. Okay. So at a certain time, whatever instruction is being executed by a computer is stored in a register called a program counter. So earlier in the instruction manual, you are seeing this. It's called a program counter. So this has only one purpose. This purpose is to serve the address of the instruction being executed. So 10100 is, suppose it is being executed, and this actually resides in the address location 02E97. So this data will be present in the program counter. So you have some kind of a state information. So at what location in your memory space is the computer residing now? And once you have, you know that this is the instruction that I am going to execute right now, this is going to go to your CPU, which is first going to fetch the instruction. So the instruction resides in memory. So somebody has to load it. So there is a hardware to do that. The hardware is going to look at the program counter. Program counter somehow tells go to that location and fetch the instruction. It is going to fetch the instruction to the some register, right? I am not going to go into that much details. If somehow the instruction is loaded, and then the instruction will be decoded by the instruction decoder. We spoke about those things. So the instruction decoder is going to tell you that what circuit will be activated that has enough information to understand that from the instruction itself, and then what are the operands, right? So if it is not a sleep operation or something that does not require operands, it is of course going to look for operands. So in the instruction itself, there could be some constant, that is not a problem. But if it is not there, let's say you want to fetch an operand from a register, or you want to fetch an operand from a memory location, you have to do that. Okay, so these are the three things that you have to do. So once you fetch the instruction, decode it, get the operands, then you have the complete instructions operands, right? You know what the data looks like. You have already loaded from the memory. Let's say you want to add 5 and 32 now. So now the hardware, you just delegate the hardware to do this, right? You know the circuit. So the add has been instructed, so it is going to do an addition. The operands have been fetched, so you know 5 and 32 needs to be added. So just give it to the processing unit. Okay, this is how it works, right? The program counter keeps track of the address of the instruction. Then the instruction is fetched, it is decoded. You get to know what are the operands that it is going to operate on. You get the complete idea about the instruction with the operands, give it to the processing unit for execution. The hardware does it, right? It's just the circuit thing that I was mentioning earlier. It does the computation. And now you have two options. Depending on your instruction, you might have chosen to write it to a register. So within the CPU, you have this set of registers. If you have chosen to write it there, you can write the result to the register, or you can actually write it back to memory. That is also an option. Okay. And now once you are done, you are stuck, right? It's just 02E97, but you want to go to the next instruction, right? Execute more instructions. So for doing that, you have something known as a controller. In the processing unit, you have one more thing which is known as the controller, right? It actually controls the execution of the program, right? Not just one instruction. You just now saw how one instruction is executed. So now you have to see how a program is executed. So after execution of this one instruction, you have to go to the next instruction. So for doing that, what the controller will do is, depending on your instruction that you have executed, it will point to the next address location. So from 0 to E97, it will become 0 to E98, right? And basically it now starts pointing here. Okay, and it will start pointing here. Now, in case if you have more than one byte, right? In this case, let's say you have 1 byte. Suppose your instruction consume 2 bytes. So in that case, it is going to increment the program counter by 2, right? If you see in this example that we were showing here, load direct from data space, the opcode normally is 16-bit, but in this case it is a 32-bit opcode, right? So the program counter was incremented by 2. So the immediately next thing after the 16-bit opcode, this is not a new instruction. This is the data of the old instruction. So if you want to execute something after this LDS, you have to look 2 spaces ahead. So PC was updated by PC plus 2. Okay, so hope this is clear how your program counter is working. Okay, and now the central thing that is responsible for orchestrating this entire show is the engine of the computer, right? That is the clock. So somebody mentioned clock in the very beginning. So this makes sure how fast your computer is executing instructions. So this is a clock pulse that will keep on the controller repeat this cycle. So this is a very boring cycle, but it is just going to do that again and again and again. So with every clock pulse that you are going to send to the controller, it is going to load the address in the program counter, increment it or whatever it needs to do, fetch the instruction, decode the instruction, fetch the operands, sometimes decode the operands, given what kind of an architecture we are dealing with, process the data, write back to the register or write back to the memory, again go to the next program counter incremented value and do the same thing. So this is something that keeps on repeating given your program. And sometimes your program runs into an infinite loop, right? You have seen, right? So the computer has no way to understand where the program ends. So if you have mistakenly introduced a bug in your program, it will keep on executing. Nobody will tell it to stop. Okay, so otherwise at a certain point of time you have to say you can like stop the controller, right? It has done executing the program, and it will it will basically enter into a state where it does not have to execute a new program. It will keep on staying there, right? So the program computer value will not be incremented there. Right, so this is a basic architecture about how a program is executed, right? Not just an instruction, but a set of instructions. Okay, any questions from here? Okay, so I'll introduce the next part, but I'm probably not going to complete today because we don't have much time left. So next thing that I'm going to start on is, this was just a very high level picture of a microcontroller, how it executes instructions, right? But we have much more than that, right? Much more than just executing programs. So there are many peripherals that this microcontroller has, which is more interesting for your IoT systems, right? So there are things like timers. So I will explain individually what all these things mean. There are ways to interface analog signals. So there are things like analog comparators. If there is an analog value that is coming in your system, let's say voltage, you want to compare that voltage with some threshold, right? And if it is more than threshold, you do something. If it is less than threshold, you do something, right? All the software control you can get. There are analog to digital converters, right, in a microcontroller. There are digital buses by which you want to interface digital sensors, right? There are SPI bus, serial peripheral interconnect. There is I2C bus. So apart from whatever we have seen so long, these are the so many things that we also package. right? And there is a lot of this IO, right? There are this input and output lines where you can directly talk from, right? So you can attach motors, you can attach LEDs, you can attach sensors to this general purpose IO lines, and somehow there are ways through something called interrupt handling, when some device has to say something to talk to the computer, or the computer has to talk to these devices. We often use things like interrupts, right? So these are the things that we are going to discuss later, right? So I won't go much more into this right now because we don't have much time left. But hope from today, what I'll suggest is, I actually have a written up thing, so later I'll do. But suggested reading, right? One thing is the instruction manual, right? These are the two things you should take a look later, right? I'll complete this thing in the next class, but at least you should look at the instruction manual, so that it gives you a real life idea about how instruction sets look like, as well as the data sheet. And within the data sheet, you just focus on only one section called the Avr CPU Core. So you can have a very clear picture about what the CPU core entails, right? What are the different components within the CPU core or the processing unit, right? You don't have to go into very fine-grained details, right? If you don't understand something, please ask me. But try to take a read, right? Light read from the manual, right? That will give you the best possible information. Right? No textbook can give you that information the manual has. Okay, so with this, I think I will wrap up today, and I'll take any more questions. If you have any more doubts, please discuss that, and then we'll close the session.